Hi there. Okay, I can go quickly. So hi everyone. My name is Ayo. Um, I'm an SRE at Google. Been working there for a year and 8 months or so. Before that I used to work in a fintech company in Nigeria. This feels like an interview intro, but yeah, I'm super interested in data structures and algorithms, and yeah, I'm just like passionate about it, and I hope people learn um, like via the stream.
Yeah. Hello, everyone. My name is Ogbonna. I am a computer science student I study in Russia, Innopolis University, and I don't really have much to say, but I'm a computer programmer. I do like computer programming contests, and yes, that's why I'm interested in data structures and algorithms. Yeah, you're welcome. Yeah.
Cool. I can share my screen. One sec. So I think Ogbonna and I are going to alternate the questions. And in general, like this is meant to be interactive as well. So we would open it a lot to the audience for comments, for people to talk about how they try to approach the question, for people to ask questions. So when we're explaining things, if there's something that isn't clear, for people to be able to like ask questions about it. Um, I guess like for me, like the important thing is that people go away with a better understanding versus just trying to rush through the questions and trying to finish everything you know within 2 hours. It'd be nice for us to do that, but yeah, the important thing is like people go with understanding. Cool. So the contest is here. Challenges, this one. So this is the first question. Can everyone see this? This should be big enough. So give me 1 sec. I want to see how the stream looks. Let me get the link. Let's see. Okay, I can see that. So I'm also on the stream if people want to ask questions there. Cool. So the question is the nth term of a Fibonacci sequence is computed as Pn is equal to Pn minus 1 times Pn minus 2 mod x. So mod is modulus. For all n is greater than 2. The mod operation returns the remainder or signed remainder of a division after one number is divided by another. So if you say 3 mod 2, I think Mark can help me here. Sorry, 1 sec. If I say 3 mod 2, that's 3 modulus 2 is going to give me 3 divided by 2 gives me a remainder of 1. So the 3 mod 2 will give me 1. So that's basically what mod is, right? Given 4 integers p0, so these are your inputs. Given 4 integers p0, P1, N, and X. Find the nth term of a product's Nachi sequence. I mean, I guess like people that have, done data structure and algorithm questions in general would have encountered like Fibonacci at some point. So this is kind of a remix of it, right? So what's Fibonacci again? Is like a summation of the number before. So if I want to get P of n, Fibonacci would be P of n minus 1 plus P of n minus 2, basically. But this one is kind of a remix. So yeah, we get the inputs with all these numbers. So P0, P1, so the first and second number in the sequence. We get n, we get x. N represents the term, the nth term that we want to get, and x represents what we mod against. So our constraints are P0 can be any number between 1 and 10 raised to the power 4. 10 raised to the power 4 is, I think that's 10 raised to the power 4 is what? I forget, 10,000, right? So between any number between 1 and 10,000, P1 can also be any number between 1 and 10,000. N can be any number between 1 and 1,000. And X can be any number between 0 and, N can be any number between 0 and 10,000, 1,000, and X can be any number between 0 and 10,000, right? So these are pretty big numbers, right? So if like we have N getting up to 1,000, it means that I can ask for P of 1,000, right? And potentially, if I'm asking for P of 1,000 and I'm multiplying, I'm only giving the first two, so P0, P1, it means that I need to keep multiplying until I get to 1,000, like if I'm going to brute force this anyway. So that's just something to think about, right? So for the given input, the output should be an integer P of n. Yeah, so that's the number we're looking for, the nth term. And so this is sample output, right? So we have 11 would represent our P0, 12 would represent P1, 0 would represent N, and 997 represent X. So it means that we're looking for the 0th term, right? And this one is kind of straightforward. So you're looking for the 0th term. You're already giving that as part of the input 11, so you just return that, right? So that one is kind of a cheat. This one is looking for the first term. You're also giving that in the input, so you just return 12, kind of a cheat as well. So this one is where the interesting case comes. So you want to find the 5th term. So yeah, n is 5, P0 is 3, P1 is 4, and the number to mod against is 997. And so the output is, the 5th term is 725. So let's see how we get that, right? So P0 is 3, P1 is 4. To get the next term, remember our formula, we do Pn minus 1 times Pn minus 2 mod x. So if we want to get P2, we have to do Pn minus 1, which is 1, times Pn minus 4, minus 2, which is 4. So P1 is 3 and P0 is 4. Sorry, P1 is 4 and P0 is 3. This kind of got mixed up, but yeah, it doesn't matter because it's multiplication. But you basically want to multiply 3 and 4 to get the answer there. Pn minus 1. This is interesting. Pn minus 1 times Pn minus 2. So if this is P3, then that's P3, P2, P1. This looks a bit, I'm not sure if this is problematic. It looks a bit odd. So if this is P3, P3 should be P2 times P1 mod X. So what is P2? P2 is 12, P1 is 4. Okay, it's fine. It works well. Mod X, that's 997. That gives me the answer. Then P4 is, we get, that's P3 times P2. So P3 is 48. 2 is 12. And so, yeah, we just keep going, until we get to P5. So yeah, that's basically the gist. So we just need to write some algorithm that helps us achieve this. So I've done like the due diligence to like write, we didn't add like main for Java, for example. So in this part, we need to get the input. So I've done some work beforehand to just make sure like we don't have to write input stuff. So basically what this is doing is pretty straightforward. We're just like reading the list of integers, which is, all of these things that you see here. And then, give me 1 0. I don't know. Someone has a question. Yeah, please zoom in a little. Okay. Is that zoomed in enough? Okay. So I'm going to print just to make sure that we are getting what we're meant to get. I'm just going to print this out, run this. Can I find symbols? I need to import some stuff. Give me 1 sec. So all of this is not too interesting. I need to read the input in Java, and I need all of this to read it. This is telling me the no stable method for writes cannot be converted to, okay, I think I need to just string the value here. Value of, I think. 1. This needs to turn exception. Yeah, Java is a great language, to be honest. It's very, you need to see everything. Okay, cool. So I'm printing out the input so that you can see that we have it, we're reading it correctly. So we have input 11, 12, 0, 97, and this is what we have in our list. We have, 11, 12, 1, and this is what we have in our list, so on and so forth. So we're reading this correctly, right? So we want to take these numbers and, come up with an algorithm to that solves our problem, right? So let us write something. So we know that we want to return a number. So right now we will just call it an int. Okay, that's it. So we don't want to return a number, call it an int. We just call this method product nachi. Product nachi, we know that it takes in, our input is P0, P1, N, and X. So we just, put that in our, as part of our argument, N and X, right? Okay, cool. So before we write code, right, let's just see how, what are we going to write, to be honest? What is our approach here? So we know that to get Pn, we need to do Pn minus 1 times Pn minus 2 mod X, right? That seems fairly straightforward, right? And at each step, we're meant to pass on. So if I do, so at each step, we're meant to pass on so let's just say, give me 1 sec. Let's say this is 4. This is 3, and this will be 2, right? So if I have P5, I would be doing P4 times P3 mod X. All right. So I would basically be doing, I would be passing on the first number. So that's P3. And I'll be passing on the value of P4 to P5. So I can take, this kind of looks like recursion in my mind, right? So if I take, if I remove P4 like from here, I can replace P4 with this, right? Then if I know P3 is P2 times P1. Sorry, this is not correct. Give me one sec. P4 is this whole thing, not just that. Yeah, and P3 is this mod X, right? And so on and so forth, right? So this looks like, it looks a lot like recursion. So for example, everywhere I have P3, I can replace P3 with P2 and P1. So this place I have P3, I can just put P2, P1 there, and so on and so forth, right? So the general idea is I calculate the current N, or in my mind, like one way I can do this is calculate current N, right? Then pass in the value of current N and P, what would I call it now? And N minus one to next recursive function. If it doesn't make sense at any point, please feel free to ask me questions. So basically what I'm saying here is, when I calculate, let's say I'm starting from P3, right? I want to get P5, but to get P5, I need to calculate P3 first, right? So here I'm basically saying when I calculate P3, I would pass in the value of P3 to P4 because P4 needs P3, and then I'll pass in the value of N minus one. So N minus one at P3 is P2. So P4 needs both P3 and P2 to be able to, get itself. So at each point, I calculate the current N. So I'll calculate P3 in this case, for example, and I would now pass in the value of P3 and the value of P2 into the next recursive function. All right, so let us, that seems kind of straightforward. Recursive, time complexity for that would probably be N, O of N. So whatever the number N is the number of times my recursive function is to be called. There's only one branch at each point. I'm only doing multiplication operations. Like all of this is constant. Like these are all like, arithmetic operations. They're all constant. Yeah. So okay, so I know that N is the number I'm looking for, right? Like that's the number I'm looking for finally. But I need to keep track of how far I've gotten. So if I have N is the max, is the number I want to get. So I want to get the fifth. So if, for example, this is 5, right? So it means I want to get P5. But I need to keep track of where I am at the moment so I can know when I've gotten to P5, right? And I'll use that as my base, what do you call this? Base, my base case. So one way I can do that is by passing in 2. So I'll pass in a value that I'll call it current N. So current N is basically going to tell me where I am with regards to where I want to get to. So this is max N. I'll just call this max N, right? So max N is the final N I want to get to. Current N is where I am at the moment. We know that we have P0 and P1. So current N should initially be 2, like, right? So yeah, we'll get there, but because we have P0 and P1, the first current N, when we call it here, should be 2 because we have like all we need to return it. All right. So let's just do this. Our base case is if current n is equal to max n, then we want to return, what do we want to return? What do we want to return? P0, yeah, this will be P0 times P1 mod X, something like that. So once we know that the value we're looking for is our current one, we just return the value at that point. I mean, we can come here to like modify later, but yeah, we just want to return the value, right? The next thing we want to do is, okay, so something else I can do is I can just get the value. Sorry. Get the current value. I would make this current value, right? If current n is equal to max n, I just return current value. All right. If it is not equal to max n, then I want to return, I'll just call product Nachi again, right? And this time, like I said, I want to send in, so when I calculate, where is this? When I calculate n, I'll pass in the value of the current n and n minus 1. So in this case, I'll pass in current value and n minus 1, which is P1, right? And then current n would be whatever current n is plus 1, right? And max n remains the same. And x also remains the same, something like this. So this is pretty straightforward, right? So we're just taking, at each point we're calculating, we have like the we have the formula. We take the formula, calculate the value, and if the value is not the value we're looking for, we just return. There's one other base case that we could be missing, right? So if, for example, max n is equal to 0. So if we're looking for the 0th term, we don't need to do any calculations because we already have P0, right? So we just return P0, right? And if max n is equal to 1, we don't need to do anything here as well. We just return P1. Right, so yeah, does this make sense at this point? Like, does anyone have questions here? Anyone confused about anything at this point?
Sorry, I joined like a bit late, so could you just go over the question that we're trying to solve again? Because maybe just read it once so that I know what exactly we're trying to solve. Question.
All right, cool.
Sorry.
I can do that. No worries. So the name of the question is called Product Nachi. It is a flavor of Fibonacci, I guess, with a twist. So when we want to find Pn, what we're basically going to do is multiply Pn minus 1 by Pn minus 2 and find a modular of that against x. So we're going to, when we get our inputs will be P0, P1, n, and x, and we're basically meant to find the nth term, right? And then we have a bunch of constraints here. P0 can be 10,000, P1 can be 10,000, n and x, n can be 1,000, and x can also be 10,000, right? So the method I came up with here is at each point. So this like looks like very recursive to me, or it looks like recursion can greatly improve, like help you exit. What do I want to say? What's the English here? Recursion can help you write an elegant solution for this, right? So at each point, or in each recursive step, you just calculate the current value. If the current value is the one you're looking for, you return it. If it isn't the value you're looking for, then you call the method again and pass in that current value, which will be n, and n minus 1 that was passed in previously, right? And yeah, you keep doing that until you get your n. Does that make sense?
Yeah, it does.
All right, cool. So yeah, this seems pretty straightforward. So I'm going to try and execute this now. Should work, I guess. So I'm going to have like, I've gotten like the inputs here. So I'm just going to have like a results tab, right? A results variable, sorry. And call product Nachi and passing in input. No, sorry. Okay, one sec. So I have P0 as int input dot get forward. All right, cool. So we know we have 4 variables here. We have P0, P1, we have N, X. N is the 3rd one, and X is the 4th one, right? And so we just pass those in. So P0, P1, N, and X. Cool. So we get that, and we just print the value here. All right. So let's run this and let's see. Cannot find symbol, current value. Why can't it find it? Okay, int. I didn't add a type. Method cannot be applied. Why is this? Why is this? Why is this? Required 5 inputs, getting 4. So I need to pass 0 here, I think. Yeah, so current N should be 2, sorry. Yeah, so the first current N should be 2. If anybody's confused as to why, please ask me. But I explained earlier why that should be 2. It's still asking me for something, right? So this should be static because Java, you know. All right, cool. So this is wrong for some reason. So my code in has a test case 11. This is returning 0 somehow.
So I think it's line 52, 53.
Right. This is okay. Yeah, thanks. I see this. So cool. So this passes the first and second one, but it's not past the second one. Why doesn't it pass the second one? So let's find out. This wants to find the 5th. This is our inputs. Right, so let's see what happens. So when this enters, the first thing I guess called here is product Nachi. P0 is 3, P1 is 4, current N is 2, max N is 5, and X is 3, right? Sorry, what did I just do here? X is 997. So this is what gets called first. Can you zoom in from your end? Yeah, I can. Is it clear? I think I need a wider screen, but yeah, is this clear? I hope this is clear. All right, cool. So what happens here? This is returning, what is it returning again? 768, which is more than we expect somehow. So let's find out why. So we do, we check if max N is equal to 0. If it's 0, return P0. If it is 1, we return P1. These are not the problem, I think. And then in current value, we redo P0 times P1 modulus X, right? Which sounds like what we should be doing. If current N is equal to max N, we just return the value. If it isn't, we just call product Nachi again with the updated values and updated N. Kind of sounds.
So, sorry, on line 27.
Yeah.
Shouldn't we be swapping current value and P1 like their positions? Does that
Yeah, exactly. That's good. Yeah, we should. Because P1 now becomes
The
N
older
minus
one.
1. Yeah, N minus. No, actually. So that's interesting. So P0, Pn, like we said, is N, Pn is equal to Pn minus 1 times Pn minus 2, right? So if I calculated 3 at this point, so 3 minus 1 and 3 minus 2, that's correct, right? So then if I want to get P4, which would be the next step, then I would do, what will I do? P3 times P2. Right, so this is what was informing my logic for adding current var to 1 to, so if we say n minus 1, n minus 2, then what was informing my logic was P3, the value of P3 should be first and value of P2 should be second. But let's see, like, how does that affect anything? So if, before I change it, it was like this, right? So if I pass in P1, current value and P1, then it is seeing this as n minus 1 and this as n minus 2. I see. So when it does current value in the next step,
I think P1 needs to change inside the method, and current value also needs to. You were already changing color value inside the method. P1 needs to also change inside the method.
P1 needs to change inside the method. What does that mean?
You need to assign P1 to. So right now we're always using the same value of P1 that we're passing in originally.
Yes, exactly.
Yeah. So we need to be changing it inside this method. We need to be assigning it to, let me see. We need to be assigning it to, we need to get the last two terms, or the last two previous, the
Yes,
last
like
previous
a
two
previous
previous
current
values.
value,
Yes.
like the previous value of
Yes.
the term.
Right. So previous value of, so here we have P0, P1, right? When I want to do P, so this gives me P2. So when I want to do P3, I need to pass in what? P2 and P1. So I need to pass in P1 and P, so I'm passing those in here, but I need to know if, so does switching it like this help? Give me one sec. It does, but why does it help? I'm not very sure, actually.
I think
Because
that's where that shifting Ace was talking about, that's where it happens.
that what? Sorry.
The swapping of the current value of P1, it happens like where you pass it
Yeah.
in is where it happens.
Yeah. So when we're doing for the third term, right? P1 becomes the new P0, right? And then current value becomes P2. I
Right.
don't know if you
P1.
yeah.
I mean, I get that. So the P0 now becomes P1. P1 now becomes current value, right? We pass this in. Okay. Something I'm not very clear about here. I'm not sure how the switching, and this is kind of odd, like, because I solved this question, but this is kind of odd. So I'm not sure how the switching affects anything here, right? Because if I'm passing P0 and P1, I'm multiplying them, then at each point I'm passing in P1 and current value anyway into the next method. And so when I get to current, yeah.
Yes, sir. I wanted to try and explain what the other person was saying. He said that we needed a way to have to save the previous current value for in the next calculation, and switching P1 like we did now. Okay, let me say in the first instance when we had P1 at the location it was, we're using the same value of P1 for every recursive call. But when we switched the position, the current value became our P0, and that was stored in the next recursive loop. And then
So every time we do this, right, P1 is going to be the same number, like value for P1 at each point. It doesn't matter what. But if we do this, then P1 gets updated to current value at each point.
Yes.
And then P0 becomes P1. Okay. Yep, that makes sense to me.
Yeah, but I don't think it's complete yet because we
Okay.
still need to be changing the value. Remember, for each run of the method, right? P1 has to be updated.
Why does P1 have to be updated? Sorry.
Because so imagine we're doing for P4 now.
Yes.
Imagine we're doing for P4.
Yeah.
Right. So for P4, I think we'll have to be doing P3 times P2, right?
Yeah.
And so the P1 that we're using here we need to be able to update it to P3. I don't know if that makes sense.
No. P3, like P1 is just a variable. Okay, I think something's confusing. So I'll call this previous.
Okay.
And I'll call this previous. Right. So it being P1 and P0 doesn't really matter. Give me one sec.
Yeah, but what I'm still saying is that
So, I think to make your point, let's think of say P8.
Yeah, P8. That'll be P7 minus P6.
P8 would be what? Sorry. P7.
P7 times P6.
P7 times P6, right? Yeah.
Yeah. So all of this initial
before we get to P8, we need to get P7, right? And from P7, we would have what? P6 and P5, right? And there's like the mod at the back, right? So when you get P7, you just need to pass in P7 into the P8. Like when you want to get P8, you just need to pass in the whole P7, like the value here, there. I need to pass in P6. So it's like when we get current value, that would be P7. So for example, let's say that in this context right now, we're calculating P7. So current value would be the value of P7, right? And then previous, which is the previous value, like which would be P6 at this point, would be what we pass in to our for our next call. Does that make sense? So P6 would take the position of P0, or sorry, I think P0 is confusing here, but P6 and P7 are the values we now need to get P8, right? And so if we're going like P9, it's kind of the same thing. So we don't actually need to modify anything apart from just getting the value we need. So here, for example, we've gotten P8, and we know the value of P7 from the last call. Does that make sense?
Sorry, I have a suggestion.
Sure.
Another angle how to solve this. What if we have a loop that iterates over n? So
we have
while
using a loop is for sure will solve this, but I think let me see, does the challenge explain this? The focus was kind of to help people get better recursion. So I mean, it's easy to solve this with a for loop for sure, because this is, we just need to update the previous value and pre-value and have a loop that goes from, I don't know, 2 to n or something. But that would be fun. So this is meant to help you improve recursion with simple problems to harder problems. And yeah. But yeah, that would work. Using a loop would work.
okay.
All right, cool. So this looks like it works. Does the person that was talking about updating P1, does the current state make sense to you?
Let's try it out first and then let's see.
Let's try what out, sorry?
I said let's try it out first.
Like the solution, yeah?
Yes.
All right, cool. Let's submit. Let's see what happens. Where are we? Okay.
But before we go further, I think we're always updating P1 technically, because P1 is the current value, which is always changing.
Yeah, P1. So
It's the current
Forget P1. That's what I'm saying. So think about it as P1 and P0 might be confusing. Like I might have been the one that confused people. Think about it as previous value and previous value, right? I need to multiply previous value. So my formula to get, give me one sec. Oh, sorry, this is the solution. Oh, damn. Okay, give me one sec. Let me copy this out. I can't edit this for some reason. Okay, copy. I think if I go back here, it won't allow me. Yep. All right. So I think like what was confusing. So let's say if we give the formula as current value is equal to previous times previous, right? Mod X, right? And at each point, current value becomes previous and previous becomes previous. So if I want to get current value, so yeah, if I want to get current value, the next current value, I would just call this current value 2, for example. What I would be taking would be current value times previous mod X. Does this make sense?
Yeah, yes, makes
Yes,
sense.
it does. It makes sense.
Yeah, all right. Cool. So yeah, automatically we're updating previous with current value and previous with previous. So we don't actually need to do any assignment. All right, so Ogbonna is
Yeah, I
gonna
have
take the
a
next.
question.
Sure.
Yeah, so I would like to understand how you get the first base case, current equals to the maximum number.
This one, this third base case.
Yeah.
Okay, no. So this one is meant to be, so you know, if we're trying to find how to explain this. If we were using a loop to find this, right? So if we're using a loop, right, we'll be going from I is equal to 0 to, or I is equal to 2. The reason why we're going to be starting from I is equal to 2 is because we already have P0 and P1. So if anyone is asking for the zeroth value, we'll just return P0. If someone is asking for the first value, we'll return P1, right? So if we don't have, is like what they want is neither 0 nor 1. Let's say they want to ask for 5, for example. We would go from I is equal to 2 all the way to 5, right? And then we would, you know, keep updating our, like we'll have two variables that we're updating basically. We keep updating our previous and previous, use it to calculate current value, you know, in a loop. Now, this is what I'm trying to simulate with recursion, this like loop type thing, right? So you need current n to know where you are. So for example, if we're thinking about it as a for loop, right? Current n would start at 2, and maximum n is the maximum we're going to get to. And so at each point, I'm increasing current n by 1, which basically in a for loop would represent another like, what do you call it? Another iteration of the loop. I think that's what it's called. Another iteration of the loop. And we want to only keep we only want to keep incrementing this until we get to maximum n. And so this base case is checking. If I've gotten to maximum n, it means that I now have my nth value. And once I have my nth value, I don't need to proceed. Does that make sense?
Yeah, it does. Thank you.
All right, cool. So I'm going to let Ogbonna take the second one, and then I'll come in afterwards. So Ogbonna, do you want to share your screen?
Yeah, sure.
All right, cool.
1 minute. Should be visible now, I guess. Can you see my screen?
No.
I can't see your screen. Huh?
Oh. For some reason, I don't know. Just tell me when you can see. I think what's wrong.
Yeah, maybe like, do you want to try and join again?
Okay, I'll join again now. Is it visible now?
No, it's not
That one
working.
also.
I don't know why.
I think I'll switch browsers. Maybe you can go on with the third one, then I'll switch browsers.
Sure, let me do that.
Mm.
So find Bob. Okay, let's enjoy that one. That should be fun. Can people see my screen?
Yes, we can. Oh.
Okay, so this one should be interesting. There are only 9 submissions for this one. So yeah, I'm hoping people leave here with like a bit more understanding on this question. All right, let's go. 1 sec. Give me 1 second. One sec. All right, cool. So on a 2D grid, Alice and Bob were playing hide and seek, and Alice has now lost Bob. All right. So you must decide if Alice will ever be able to reach Bob from her current location, given the 2D grid Alice and Bob played in. On the 2D grid, there are 4 different types of cells. A cell with a character A representing Alice's current location. A cell with character B representing Bob's current location. Cells with character full stop. Sorry, representing an empty cell. Cells with character what's this called? Hashtag hash representing a wall cell. To reach Bob, Alice can now move right or down and must pass through only empty cells until she gets to Bob. She can't go through all cells, right? So she can only go through cells that have full stop, and she can't go through the ones with the hash. So this is an example scenario, right? So Alice is here, A, where A is, and Bob is B, where B is. Alice can go through all of these places with the hash, but she can go through like these places with the full stop, right? And remember that she can only move right or down. So, she can move right to this point, which is a valid move. She can move down at this point, which is valid. So, and she can move right down to get here, which is valid. All right. Determine if it is possible for Alice to get to Bob by moving only right or down and passing only empty cells till she gets to Bob. Output a string yes if it is possible, or string no otherwise. The initial locations of Alice and Bob on the grid are not fixed. They could be anywhere. So Alice could be anywhere on this grid, and Bob could also be anywhere on this grid, right? Cool. Let's see, what else is interesting? So input format, we have the first line of the input contains 2 integers, n and m, representing the dimensions of the 2D grid. N represents the number of rows, and m represents the number of columns. the following n lines contains m characters representing characters in the grid. All right, so basically what they're saying is the first line of the inputs gives you the number of rows, and the second one gives you the number of columns, right? So we would have 4 rows, so 1, 2, 3, 4. And on each row, we would have 5 characters, right? So this is just like a way to read the inputs. Then for constraints, we have n can be anything between 1 and 1,000. M can be anything between 1 and 1,000. So we can have, and the maximum of n times m is 10 raised to the power 5. Okay, so that's kind of limiting, because if this limit wasn't given there, then the maximum n times m we could have would be 10 raised to the power 6. No, sorry. Yeah, 10 raised to the power 6. That's 1 million. So 1,000 times 1,000. But this constraint is there that says it's just 10 raised to the power 5. I don't know that it matters much, but I guess we'll see if it affects how we think about the solution as we go. The output format should contain a string, yes, if it is possible, or no otherwise. Beware of capitalizations. The string should all be in uppercase. Cool. So let's see. How do we explain this? So sample input is this. So Alice is, I think this is just this one that they showed here, right? I think so. Yeah, it's just that represented in, I guess, a non-visual format. Okay, then we have another input here. This one could be interesting. So as you see, Alice can only move right or down, and on her right there is a wall, and on like at her down direction there is also a wall. So there's no way she can move from her current position. So yeah, there's no way for Alice to get to Bob at this point. All right, cool. So how do we think about this problem? Does anyone like want to come in to explain here? Anyone have ideas?
Okay, so I was thinking of like it would be a recursive solution, probably depth first search.
All right, so a couple of things you said. It would be recursive, it would be depth first search. Give me a sec.
Okay, so like should I say how I would go about it?
Yeah, so a couple of questions. Why DFS?
So,
and how do you go about it, and why DFS? Yeah.
Okay, so DFS, because DFS is, first of all, I said it's going to be a recursive solution. So it means, sorry, please could you go back to the image? I want you to. So it means from where my starting point is, and for me going right and down, I want to be able to check just to my right and below. To explore possible, what do I say, possible options, like possible value paths to until I get to my answer. So that's why I use depth first search.
Okay. All right. So how would you go about this? Like.
Okay. So start with A. So for the input they gave us, I mean, so the input could start from, it might not start from 0, like cell 0, 0. It might start from cell 0, 1. So initially, I'll have my base function that is returning my main answer. So I will do a for loop and check, okay, if.
No. So don't try to write. Don't try to. Yeah, just speak the code to me, right? Explain what you want to do.
Okay, so I would first of all find where who is it? Anim, I don't know her name. Where she is initially, where Alice is. So I'll find where Alice is initially. So when I get where Alice is, then I'll recurse on, like that's the valid path. So I'll recurse on that position, that's my right or below me.
I would
I'm
recurse on that
calculating.
solution. You would recurse on that solution. So you would recursively, I think recurse on that solution is a bit confusing. So you recursively do what?
So I'll recursively go down. So if I see a value, so first of all, when I get the position of Alice, I'll recursively go to my right or below to explore other options, like trying to get to Alice.
All right. So you would go right or below until like to try and get to Alice.
Yes.
All right. To
Explore
try and
my
get to
right
Bob.
or below to get to Alice.
Bob.
I'm sorry, to get to Bob.
All right. Until you get to Bob. Okay. So how do you kind of end this? So when you get to Bob, right? That's one way. That's one way. What's another way to end this?
Oh, it's my base case. Also, the other way would be if I eat. Sorry, could you go back to? Yeah, like so. If I eat a wall, if I eat a wall, that should be a base case. That would end my recursive function. And also, if I'm out of bounds of my grid, of my matrix, like if I'm out of bounds, that should end my recursive call. So.
Okay, out of bounds. All right. So, anything else here?
No, that's basically how. I think that's how for now.
All right, what's the
That's how we go about it. Hello.
Hi, I said, what's the time complexity for this solution?
Oh, okay. So my time complexity. Let me see. So if I'm recursively calling, so I think it would be raised to power. Okay, so let me see. I'm calling. It's going to raise to power n, where the n is length of my grid. So is it going what do you call it? My length of the column and row is going to be the same.
Your length of the column and row.
Yeah.
No, no one said anything about it being the same. So it might be the same, it might not be the same.
Okay. So I think I really have issues with my complexity, but try for recursive functions. But I'm thinking, so if it won't be the same, that's length of m, like one length of my outer array and length of my inner array, or length of my row and length of my column. But so that I know that would be like a time complex. But I also have issues with, because I know recursive functions have raised to power. So that's the one I can't figure out. I was hoping to ask you on this call.
Okay, this is interesting. So I think, I might be wrong. We'll try and see how we can get to that. The time complexity of this is 2 raised to power n plus m.
2 raised to power n plus m.
Yeah. So I would 2 because there are 2 branches. At each point, you're recursively going right or below. N plus m because in each branch you can check the whole grid, like the whole. Sorry, not n plus m, but n. Is it n plus m? I'm actually not sure whether it's n plus m or n times m. That's something I need to confirm. But yeah, give me 1 sec. I would try and clarify this before we go. I'm not thinking too clearly yet. But yeah, I think that 2 because we have 2 branches. At each point we would go. Okay, no, this is 2 times m, not 2 plus m. Yeah, this is 2 times m. Because n times m, right? So if we have let me see if I can explain this with Scarlet Draw. Let's see if this makes any sense. All right. All right, cool. So let's say that we start at position 0, 0, right? At position 0, 0, we can go. I don't even know what's the best way to explain this, to be honest.
I think with a tree or something.
Yeah, probably a tree, but I'm wondering what number to start from. I mean, a tree is what I would use to explain, but I'm trying to think about. Okay, just let me think about this. After the solution, I'll come back to it before we go.
Okay.
But yeah, the idea is, so I mean, this idea sounds good to me. Does anyone else have like a different idea or think we should do it differently?
I wanted to ask a question about the time complexity.
Sure.
Could it just be n times m, since we move over those boxes just once across the entire grid?
No, but we don't move over it once though, do we?
Yeah, we do, since there's a constraint on the direction we go.
We move through them once since there is a constraint in the direction we go. Right. Well, actually, right. Yeah, we do not go right. Yeah, that's correct. We don't go up. We don't go down. So we can only go right and down, right and down, right and down. There's no point at which I can go right and down. Yeah. So the only way I can ever get somewhere is so okay, no, it's not just once. So let's imagine something. Yeah, I mean, it sounds correct, but not really, I think. Let's imagine something really quickly here. So let's imagine we didn't have any walls, you know. Is this copied? Yeah, it's copied. Cool. Let's imagine we didn't have any walls, right? Okay. Now let's say I was starting at this position. So start here. I'm starting here, right? And I want to get here. And how many ways can I get here by going right and down, right? So by getting to end, I want to get to end. There are no walls around me. How many ways can I get to end from start? So let's see. I can go like this, right? And go straight down. Right. Okay. I can go like this and go straight this way. I can go like this, then go down like this, then go this way, right? I can go, down, right? Then I go straight like this, then I now go down this way. Now you see that this point, I have already touched it twice. I can go, there's even one point I've touched 3 times. I think it was this one. It was this one. So this one, I touch it, I can go from start, I can go this way, then go down. That's even 4 self. So let me delete this. So I can go, can I use different colors to maybe explain here? Yes, I can. Give me 1 sec. Sorry. This might not be super clear. Give me 1 sec. I think I can use different colors, yeah, to explain what I'm saying. So I can go this way. Abi, I can go this way. I can go this way. I can go this way. So here, like this thing, I've already passed the space 3 times. In fact, I can even go, imagine, so I can go like this, like I'm going, what color did I choose just now? Green. I can go this way, go down. Okay, no, I can't go down this way because I can't go back up. So no, that wouldn't work. But Okay, that won't work. Because I can't go up. But like, for example, here I've already gone past here 3 times, and these are 3 possible ways, you know. So you can't say for sure that I'm only going to touch a cell once. You know, that's not correct. That's not a correct assumption.
Sorry, I have a question.
Sure.
Since we're just looking for like we're just looking for Alice, not as if I bothered about like the number of ways. If we just visit the cell once, can we like probably mark that cell as visited and say, okay, we visited already? Because if that cell cannot be done to Alice, then there's no point going to that cell again to get to Alice.
If we can mark the cell as, can we mark the cell as visited? Okay, how would that influence our? I mean, I don't know. Let's explore that. How does that like influence our choices? So let's see, right? Because we need to think about marking a cell as visited very carefully. I think we need to be very careful because does anything affect it? If I mark a cell as visited, is it possible that that path? So, for example, if I was going, let me one sec. Let's visualize this again, right? Did it go? All right, so let's say that this was a wall, right? So hash is here. And somehow, right, we went through this path first. So we went through this path first, right? Let's say that all of these places are walls sorry. Control V. This is not a wall. So on and so forth, right? Yeah, this kind of looks similar to the question. So let's say that we get like this is the path we check first. So along the way, right, as we're going, we can mark this as visited, right? This is visited, this is visited. We get here and we don't find it. So marking as visited you need to be very careful, because if you go down a path that is a wall or that can't get you to the end, you need to make sure you can check another path. But if you mark a cell as visited, it is possible that your like whatever solution you write doesn't check that path again, and so like all of these becomes obsolete. Like you can't check here just because this is visited and you've got into a wall.
Sorry, no, we're calling recursively, right? So we're calling recursively right and down. So if that guy is already visited, we go down and okay, it's a wall. So when we come out, we have to call right recursively to like explore that part. So that's like where I'm coming from.
Yeah, but like that doesn't. Okay, so if we're checking I'm trying to think about how this fits into what you were saying earlier, right? What you were saying earlier, yes, we have two recursive calls that would at each point either go right or go down. Yeah. Your initial point was to mark a cell as visited. I'm trying to think about how that influences our decisions, right? Does it affect anything? That's just what I'm thinking about. I don't know for sure. So I'm just thinking about if we decide to, at this point we're going right. I don't know. We can test it. It doesn't look like.
I don't think it actually affects, because we are just going through one part. We're not going up, and we can't go up, and we can't. Okay, so I don't think there's any need for the visited.
Yeah, because if we do exactly like that was my next question, right? So if we do mark it as visited, but we only pass that path once.
Path once, yeah.
So yeah, we already have a guided path, so
yes.
All right. So our question is what the time complexity is. I would leave this here. I will come back. Just give me 1 sec. So either 2 raised to this or n times m. I could be wrong. Or what was the other option? I saw something else on this call. N raised to 2. Pretty sure it's not that, but we'll just leave it. All right, let's write the solution. So I'm going to skip a few places, just put how to read the inputs. Let's go back to this really quickly. So remember, like what the input is. We get the row and column. Then next we get whatever the number of rows are, and in each row we have whatever the number of columns are. Like that's how input is. So first thing I'm doing here is reading the row and column. Then I would now read each line. So every line after that is going to represent a row in my grid. And so I just read all of the characters or strings from this line, the characters on this line, and I put them in each cell. So by the time this is done, something like hash dot hash dot something like this would be split into hash comma dot comma dot comma and so on and so forth, right? So at the end of the day we have our grid, and from our grid we can get what we want. So I'm just printing it out here. Doesn't really make any difference. Then I'm calling a method called findBob where I pass in the grid. All right, so let's do that. FindBob. All right, so what should Bob return? Bob should return, findBob should return what? And findBob should return, yeah, should return a string. Let's make it static. String and findBob. Should the string be capital in Java? Yes, it should. All right, so here I'm going to pass in a string grid. This can be anything. It can be character grid. Doesn't really matter. All right, so let's see our base case. Well, what is our base case? We don't want to go out of bounds, and we want to, when we find Bob, we want to go. So
for the base cases, should we also have a case where we eat an ash?
Yeah, that's the.
Yes,
Oh yeah,
yes.
we should. Yes, we should. Wall. Thank you. Ouch. So I can't think of a neat way. There might be a way. I just can't think of it. To return a string from this method that we want to call recursively, right? So I am inclined to yeah, because here we also need to keep track of the row and column that we're in, right? Like where we are currently in the grid. So I'm inclined to create another method that would kind of be a helper. I would return a Boolean from here. The Boolean would tell me if I can find Bob or not. And here I would, basically the same method. I'll just do like an overloading thing. Then this one would tell me the current row and current column I'm at, and it's a pass grid. Yeah.
Mm-hmm.
All right, cool. So here I just want to we need to find Alice, right? So this is what this guy said we should find Alice. So we would find Alice. We should do that. So we have a method to find Alice. The method should return, I don't know, a row and column. So the row and column can be in an array or something. We'll just call this Alice's position. Why is this commented? I can uncomment it. All right. So this would be find Alice. Find Alice would return. I'll pass in the grid here. Then what's the next thing we want to do? Something is going on here. All right. So when we find Alice, then we want to now see if we can find Bob, right? and here we're passing, we start from Alice's position. Remember, is Alice's position we're starting at, and Alice position 1 and grid. All right, cool. And so if this is not right, so if this returns true, then I want to return yes. So that means I can find Bob. If this returns false, then I can't find Bob, right? Okay. So I'm just going to write a quick one for Alice. Okay, so here what do you want to do? Just like for loops, right? So just go over like int I is equal to 0, I less than grid the length, something like that. I plus plus. So we're just going to go about the grid and look for where Alice is. Grid. Okay. So yeah, just check if A equals grid I J. So this is an interesting like choice. You know, like, does anyone know why I decided to do A equals versus the other way around? So like potentially I could also have done grid IJ, you know, equals as well. This is Java, so yeah, it's Java specific kind of. But I think it kind of applies in a lot of places too. So, I mean, I'll just kind of say it so we can go. There's no time anymore. But basically, in Java, a string can be null. I can pass in null because the string is an object. And so grid IJ could be null for some reason. And if I do null dot equals, that's going to throw a null pointer exception. But because I know what I'm looking for, I can check if that equals. So A equals null will just return false. We just return false, right? But if I did it this way, this could be null. It doesn't really matter here because we know that each cell would have like, you know, a valid character. But just in general, when you're coding out in the world, anybody can return anything to you. Okay, cool. So this should return Alice to us. If for some reason we don't find Alice, we just want to return, you know. I keep mixing this up with Go. -1, -1. Yeah, all right. So we found Alice. Now we want to find Bob. So let's see. Recursively go right and below. So how do we go right? So if we are at 0, 0, to go right, we add 1 to what? The column. To go down, we add 1 to what? The row, right? So we just, that means that we, at some point, we would return and find Bob. We know that we either want to go down grid or we want to go right. So right is column, so I'm increasing column by 1. So T plus 1 and then grid. So yeah, recursively go right and below. That makes sense to me. Then I want to do this until I find Bob. So if I find Bob at any point, I do it again. So B equals grid RC, return true. So if I find Bob at any point, I just want to return true. And you guys know like your logic tables, right? So true or false is true, right? So if one of these returns true, and the other returns false, then true or false is true. It would be equal to true. So that's why this works. All right, cool. So until you get to Bob, right? Until I go out of bounds. So I should probably check if I'm out of bounds before I check if I'm at Bob, because if I'm out of bounds, if I put the out of bounds check after this, then potentially when I check this, I could get an out of bounds exception. So I want to make sure that before I check if Bob is there, I want to check if I'm out of bounds. So how do I do that? I want to make sure R is not less than 0. So if R is less than 0, R is greater than or equal to the number of rows, which will be grid and length, then return false. If column is less than 0 as well, or column is greater than or equal to grid, number of columns, then return false as well. And at this point, I want to return true. Is there something we're missing? Wall. Yes, we're missing more wall. So I just check here. This one will just be hash. I also want to return false. Cool. So,
sorry, I was wondering about the wall-based case. There's a possibility that you can hit a wall in one direction in the right, but not on the down.
yeah, but that wouldn't affect it, right? So that means like I'm starting from current R, right, and current row and current column, right? Now current row, if let's say that down, if I go down, I will hit a wall.
Yeah.
Go down will hit a wall, but going right would not.
Right.
Wouldn't. I don't know why I'm typing this out, but yeah. So go down will hit a wall, but going right wouldn't. So this way, I'm going down, so I'm increasing row by 1. So I would be checking current R plus 1. So what I'm actually going to be checking here, if this is a wall, is current R plus 1 like this, because I'll have passed in current R plus 1 here.
Okay.
So what I'm actually checking is if the next grid, if the next cell is a wall.
Okay, makes sense.
Yeah. All right, cool. So this looks good to me. So let's see. Let's go over this, right? So we're getting Alice's position. Alice's position, we're just like iterating through the grid, finding where there's an A, returning the position, back. Then I passing that position into a can find Bob thing. I have a bunch of base cases. I check if the row is within range, column is within range. If we're hitting a wall, and I also check if we found Bob. If we haven't, we go down or we go right. Yeah, I'm going to test this. Cannot find symbol. What symbol is this?
Oh, you misspelled Bob.
Bud. Oh, right. Thanks. IO exception. I need to throw. All right. Cool. These are just 2 cases. Let's see if this works. There's a lot of test cases. Cool. Yeah, they work. It works. Cool. Is Ogbonna here? Does anyone have questions, by the way? Let me see.
Yeah, so about time complexity, I think from what you wrote, I can see that I think it might be 2 raised per n times m, because we have 2 trees, 2 branches per function. You might either go to your right or to your left. And what if in case we don't have a wall, it might extend to the end of an array of the grid. So I think it might be 2 raised power n times m for the time complexity
Yeah.
for me. Well, so what about the space?
Space complexity. Would probably be, let me see. What's the solution? V results. What is the space complexity of this? What are we storing really? Grid is, is already there. The other thing that we're going to be storing is the R and C. But yeah, I guess that there's a recursive stack, right? The recursive stack would only ever get to n plus m, I think, at each point. I might be wrong. I'm not thinking carefully about this at the moment, but let me see, sure. So if I go down one path, I go r plus 1, 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 r plus 1. So I can keep like doing r plus 1 until I get to the end, to the very end. So that would give me the length of r, or I can do like c plus 1, c plus 1, c plus 1. So my space complexity would be the maximum of n or m. So it would be something like max O max R RC or something. Or like, I mean, I guess to be safe, I can just say R plus C, to be fair. Yeah. Is Ogbonna here?
Oh, yeah, I'm here.
Can you try and share now?
Okay.
Nice.
It works now?
Yeah, it is.
Oh, cool. I think I can see some applications here in Russia, so I had to use a VPN. Okay, so I'll go for the second and the fourth problem. And I think we have to move fast since we don't have a lot of time. So the second problem is you have an array of n integers and you have some value x. And you want to count the number of subsequences having a total bitwise OR of x. So I guess we should go over a few things. What's the subsequence? What's bitwise OR? So by any chance, does anyone know what a subsequence is? Oh, I can go ahead to explain it. So I'll just go ahead to. So a subsequence of a sequence is a sequence that can be derived from the given sequence by deleting some or none of the elements without changing the order of the remaining elements. So let's say we had, is this visible? No.
Yeah,
so let's say we had some array 1, 2, 3, 4, and 5. So a few subsequences are 1, 2, 1, 3 is a subsequence, 1, 3 is a subsequence. In fact, I think we start with small subsequences. 1 is a subsequence, 2 is a subsequence, 3 is a subsequence, and etc. You should get the point. So if you delete some values, the remaining values form the subsequence. And also the whole array is part is also a subsequence. Does that make any sense?
Yeah.
Okay, so does anyone know the amount of, so let's say it's an array. If the length of an array is n, does anyone know the total number of subsequences it could have? So if the length of the array is n, how many subsequences can we have? Okay, so it's
18. I don't know.
I think there's something close to 2 raised to the power n plus 1.
Yeah, exactly. 2 raised to the power n actually. Yeah, 2 raised to the power n, that's right. Because does anyone know why? Because for each value, each of the n values in the array is either we pick it or we don't, right? So we have two choices for each of the n values. Does that make sense? So you have 2 raised to the power n in total, including the empty subsequent. So if you're counting 1, excluding the empty subsequent, it's 2 raised to the power n minus 1. Okay, so I think it should be enough for the subsequent part. And the second part of the question is the bitwise OR. It's not really necessary to understand how this works, but I can just go over it quickly. But for this problem, it's not really necessary. But we can just look at the bitwise OR table. Okay, I guess I'll just put it here. So if you have 0 or 1, the bitwise OR is 1. If you have 1 or 0, the bitwise OR is 1. If you have 1 or 1, the bitwise OR is 1. If you have 0 or 0, the bitwise OR is 0. So basically, the OR is always 1 except when 2 bits are 0. Okay.
So how is it different from the logical AND?
Okay, so for the logical AND, it's only set.
Oh, sorry, logical OR rather.
What? Bitwise OR is the same as logical OR.
Okay.
Does that answer your question? Alright. Okay, so let's go over the samples. Now we have an understanding of the problem.
Eric, please could you? All right.
Okay, so for the first test case, we have n is 3, and x, the total OR we want to find is 3, and 1, 2, 3 are the values in the array. So we want to count the total number of subsequences of this 1, 2, 3 that have a bitwise OR of 3, right? So here you can see some of the subsequences that have a bitwise OR of 3. If you, how do we do this now? Can I show something? I think I want to show something. Okay. Okay, so I want to use Python, so we can see the bitwise OR here. Is this legible enough? So if you have 1 or 2, you can see this.
Yes.
Okay, I think maybe I'll just increase it a bit.
Yes.
This way. Okay, we'll just work with this. So the bitwise OR of 1 and 2, that's A0 and A1 is 3. This stands for, this is a bitwise OR in Python. Yeah. And of course, the bitwise OR when you have just 3 is 3. And for 1 and 3, it's also 3. For 2, 3. This is A1 and A2, it's 3. And for the whole thing, the whole subsequence, the whole array, sorry, it's also 3. So these are the subsequences that have a total OR of 3. And in total, we have 1, 2, 3, 4, 5. So the output here is 5. Makes sense, right?
Sorry, I don't get how 1 and 2 gave us 3.
Okay, so I guess we can look at the bits here. Let's look at bits. So how, what's
Yeah,
one?
like I think that I mean, going into like what bits are specifically might not be too valuable here. But what you need to just know is, so these numbers here are like the decimal representations of numbers. Like, so 1, 2, 3, 4, 5 are base 10 representations. The bits operations compare the binary, like the base 2.
Binary equivalent.
The base 2 equivalents, yeah. So one or 2 is not actually compare 1 or 2 in this sense, but look at the, like, convert it to binary, do it yourself, and you see when you convert the binary value back to decimal base 10, you would have 3, right? Yeah.
Fine.
Okay, so but if you still want, like, I don't know, if you still, so we, 1 is 0, 1 in binary, and 2, this is 1. 1, and this is 2 in binary. So let's look at the OR of the first position. According to the table there, 0 or 1 is what? It's 1, and 1 or 0 is 1, and this is 3 in decimal. So that's how we got that value here. Makes sense?
All right, thanks.
Okay. And same thing for this. We want to find out the subsequences of this array. I have a total OR of 2. In this case, there are just 3 subsequences. Subsequence A2, which is it is correct. I think. Okay, yeah, 0 indexed. Okay, so A2 has 2 as a value. A4 is 2, and A2 or A4 is 2 or 2, which is 2. So in total, we have 3 subsequences. Okay, so I guess we can. So how do we approach the question? Does anyone want to share their approach on how to solve the problem? I can just go ahead. So I guess I will just go ahead. So we want to create a function to count the number of subsequences. And like I explained, for, let's use this, the input array is 1, 2, 3. So we're going to go from left to right. For each index, we'll go from 0 to 2, 0 index. So we have 0, 1, and 2 index, 0, 1, and 2. So for each index, what we're going to do there is we're either going to add it to, we're going to have some accumulated OR, and it's either we add this to our accumulated OR or we don't. So our function is going to look something like public static count subsequences, and we have the current index. We're going to have the accumulated OR, and of course we will have the array. Does this make sense?
What are we meant to return here exactly, Steph? I can't remember.
Oh, sorry. Yeah, we return to that one. And we also need, of course, a total number of subsequences, count for subsequences.
Okay, right.
Okay. So for starters, I guess we can just read the input first. So we'll read the and we have n, we have x, and we have our array. And our result is going to be count. I'm just trying to, we're going to start at index 0, and the accumulated OR initially is going to be 0. The array A, N, and of course we need X here too. So we need the target OR here too. Target OR. Does this make sense so far? Okay.
So like what's the plan here? Like at each step, what are you going to do?
It's either we add it to the OR, the current accumulated OR, or not.
Okay, and then what is your base case?
So the base case will be if our current index, if we're out of bounds, like if we're gotten to the end of the array, if our accumulated OR is equal to a target or, we're going to return 1, or else we return 0. So if it's equal to our target OR, then we increase the number of subsequences that have this OR to 1, right?
Yeah, I think we can make the if statement simpler, right? Like by checking accumulated OR first, and then if we just check current index is equal to n, then just return 0.
Okay. Yeah, that makes sense. But actually, this won't count all the subsequences. So imagine you add some prefix and you just have the OR there. Like you're not going to count the remaining for the remaining indexes.
Look to me.
What?
What were you saying, sorry?
Yeah, I'm saying this won't account for everything.
Okay, why not?
So let's say you stop at some prefix and you had the total OR, right? You still need to count the remaining ways to get like some. It won't count all the subsequent basically.
Oh, I see.
Yeah, it won't. So this has to be in here when we have gotten to the end. Yeah.
Right. I see that. I see that.
So, like I said, we have two things we can do. So, first is pick. If we pick it, count our subsequences. We move to the next index. Accumulated or the current index. The array and then also the target or. And subsequences current index plus 1. So in this case, we don't pick it. Or a and target or.
Sir, please, I want to ask a question. So, sorry, please, is there like, can you give like a rundown of what we are actually going to do first? Like, what's the plan? Is it to generate generate sequence?
Okay.
Then when we do that, we would now compare to give or I don't know what.
Okay. So let's say we're initially current index 0, right? Accumulated or let's call it 0. And our target for the O1 from this should recall from the question is 3. So target is 3. So initially at index 0, we have two options. Remember, we have 2 raised to power n subsequences, right? So at index 0, it's either we go to index 1 and our arc remains the same, and also we pass our target. So this is option 1. And the second option is we go to index 1 and we OR, our accumulated OR gets ORed with 1, and 0 or 1 gives us 1, and this is 3. Does this make sense so far? Make sense?
So, sir, our target is 3. Is that the length of our array?
Okay, I guess I should pass the length of our array is also 3. So let's see length. And is 3. So this is these are our options at index 0. So at index 0 is either we go to the next index and our accumulated OR doesn't change, we also, these ones are constants. We just pass them to the next. These are the most important ones: the index and the accumulated value.
Okay.
Okay, this is, you can think of this as 0 or 1, right?
Yeah.
So our options are, so now depending on the function, it's basically a tree. You can view it as a tree. So for every index, you have two options. Either you go to the next index without changing the accumulated or you go to the next index, changing the accumulated or with our current value. Does that make sense?
Yeah.
Okay. So we are going to have four options at index 1. So let's say option 1 got called. We came to index 1 with this option 1, right? So let's name our options for index 1 as option 3. Only this, I guess this is obvious. This case 1. So option 1 for index 1 will be index 1 and accumulated or 0. This is, we go to index 2 without changing anything, and our length is 3. Does this make any sense? This is first option. If this index gets called with this, does this make any sense?
Yes.
Okay. So if index 1 gets called with this, we have two options too. Our second option here is also option 2 will be index 2, and remember the value of position 2 is 2 and target 3, length 3. Does this make sense from our base case for index 1? That's base case 1. Base case 2 is this. If we get called this value, our option 3 will be index 2 with at 0, 1. Remember, we don't change anything. For option 3, we don't change anything. And target 3, constant, length 3, constant. While option 4 will be index 2. And for our accumulated value, we're going to add 2. And our targets, and this remains constant. So far, does it make any sense?
Yes.
Okay. So that's basically what we're doing. So it's basically a tree, and for each node in tree, you have two options. Either you pick it or you don't. Right? Okay.
Yeah, this also kind of like directly feeds into the time complexity for like how we would explain time complexity for the previous question as well. We always have two options at each step.
Okay. So I guess it's better I name this option 1 and this option 2. So the total number of subsequences will be the one. Either we pick it. That's option 1. When we actually, this is, we're going to replace this. It's quite different from what I explained. This will be accumulated instead. Okay, so this option 1 is if we don't pick the current index, and this is if we pick the current index. Okay. So our total is going to be, total number of subsequences will be option 1 plus option 2. Does that make any sense?
Can you like come in? Is that the end of our solution?
Yeah, basically.
Sorry, can you come again from like beginning? I want to pattern it well.
Okay. So I said we have an array. This is our array. The array given the input. Our target for x was 3, and our length is 3. We said subsequences of an array, like it's either we pick or we don't pick, right? That's how you count. That's how we arrived at this series per n. For each index, we have two options: either we pick it or we don't. Right?
Yeah.
Okay. Now we want to go from left to right, from the first index to the right index. Sorry, to the last index. Now we have some. Initially, we're at index 0. We have an accumulated OR, which will be 0 initially. We have the target, which is 3, the length, which is 3. All right. So at index 0, we have two choices. Our first choice is we move to index 1 without changing the accumulated value. The target and the length remains the same. Our second option is we move to index 1 and we take the current value. Remember, the value at index 0 is 1 here.
Yes.
Okay. So we have two options at index 0. Does that make sense? Does index 0 make sense so far?
Yes.
Okay. Now at index 1, remember, when we're going to index 1, it can be called by either of these options.
Yes. I get
So
that.
if
So
you
that
are
means
like,
we can always, we can even skip index 1 for when we're in index 2. You can also skip index 1. Can skip
so,
picking
yeah, if you
index 1.
visualize as a tree, you have like two branches coming out of index 0, the node index 0. So let's say we came to index 1 with this, with option 1. Let's say we came to index 1 with option 1 from index 0. Yeah.
Yeah.
So our first option at index 1, we move to index 2. Our accumulated value remains the same. Our target and length, these are constants. You don't need to put that. Now our second option will be we move to index 2, but we take the value of index 2, which is 2.
Yes.
That makes sense, right?
Yeah.
Okay. Now let's say we came to index 1 with this. Remember, we came to index 1 with option 2.
Yes.
Okay. So if you came to index 1 with option 2, we already have it. We have accumulated this already. So we can go to index 2 without changing what we have accumulated so far, this. Or we can go there by adding, we add OR to the answer. Like the accumulated OR and the OR of this current index, which is 2.
Okay.
So you can just continue, it continues going down that way till we eventually come to the, eventually we are going to get to like index n. And now let's discuss the base case. So when we get to index n, we're going to check our accumulated OR is the target OR, like the OR we are looking for, which is x. If our accumulated OR so far is equal to target OR, then we return 1. If not, it's 0. 1 means we're going to increment the number of subsequences we have seen, like number of subsequences that have this OR, and 0 means we're not going to increment it because the accumulated OR doesn't match the target OR. Okay. So yeah, I guess that's how the scanning pipeline.
I think you just need to put new.
Yeah. Okay. It's not working, I guess. Yeah, that should be it. Count all. So. Okay. They should be it. I'll try. What's the problem?
What's the complaint about?
It's undefined.
Yeah, I meant to pass an array somewhere. Are you passing a okay? Is an array
Yeah.
passing now?
Maybe doesn't match signature somewhere. 0, 0, A and X. 0, 0, A and X. Yeah, I think that's gone. So we can test this on the inputs. Okay, yes. I can just type it. 3, 1, 2, 3. Yes, so the answer is 5 here. And we can just copy this and here. I think I need to name of my class has to be solution. Solution and make it public. Okay, so it passes the samples and we can submit. Okay, so that's the correct solution for this. Now maybe I'll share this in the chat. Yeah, I'll share it after the session. Do we have enough time to go over the last one?
It's 5. It's almost 5. I don't know.
Yeah, it's almost 5. So maybe I don't know.
People. Although what do you think about like doing the number for next week? I feel like that one actually needs some.
Yeah, it's a bit difficult.
Yeah, it needs some explanation. Sorry? All right, cool. Sounds good. Yeah.
Can we get the solutions? Is there a way we can see, can go back to the question?
Yeah, I'll share them after this.
Yeah, we can share the solutions.
Yeah, please, the solutions.
I'm sorry, please. I'm on general chat, but I'm not on the DSA channel. I don't know. Yeah, thank you.
Thanks a lot.
Bye.